Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi ajma'in. Assalamualaikum and a very good morning to everybody. Welcome to TNB CIRED ACEM knowledge sharing on the topic of a review on transformer oil diagnostic using the dissolved gas analysis technique. 2nd December today. You are with me, Muhammad Rashid Zainal Abidin, senior engineer, become your host for this morning. So okay, thanks, Mr. Faris for the speech. Okay, let me start our session this morning with the recitation of Al-Fatihah and Doa Al-Fatihah. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma salli ala sayyidina Muhammadin tibbil qulub wa dawaiha wa afidil abdan wa shifaiha wa al absar radiyallahu anhu ajma'in. Allahumma ftah alaina hikmataka wa anshur alaina min khazin rahmatika ya arhamar rahimin. Rabbana atina fid dunya Allahumma ftah alaina fatul arifin wa anshur ala rahmatika wa zakirna mahsina wa liman ladayna ya arhamar rahimin. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin. Okay, how are you today? We would like to welcome everybody to join our Slido for poll today. So before we start, let's everybody come and join. You can either go to slido.com website or you can just scan QR at the screen. So we welcome everybody to join us for poll today before we start our program, our session this morning. Thanks, Greg. Okay, thanks. Sorry, I see we have about 40 plus, 43 or 44 of the participants today. So we are still waiting everybody to join our poll today. How are you today? So the weather at my home today is cloudy. So don't let your weather overcome you. Your sense is good today. So still welcoming everybody to come to join our poll for just to chill out to make our mood. Okay. We have clicked from TNB and also from outside of TNB. So welcoming everybody to come to join this session today. So most of us feel good and great. Alhamdulillah. So keep strong, stay cool. Okay. Okay, let's go to the second question. May I know where you come from or which industry are you attached with? Are you from TNB or are you involved in telco or for oil and gas? Maybe from academy. So we like to know more from TNB. I think. So because this webinar is open to public as well, to the direct members for the privacy, but still open to everybody. So we are starting everybody. I will welcome everybody to share to the link or the so together take some advantage or knowledge, extra knowledge for regarding the transformer. Okay, never mind. Got a few from academic and from other countries. So my friend from TNB, can you share the event to your colleague or your friend so we can together gain some knowledge in the transformer? Okay. Can get benefit from this event. Got the okay. I'm not really sure how's the maybe some might. Okay, I'm not sure how the okay. So if the line of the sound is okay or if the video is okay, and then we get some emotion or emoticon from everybody. Just to know how's the line. Okay, we go to the next question. May I know, are you a CIRED member or not? Yes, yes or no. Welcome to, even you are not CIRED member, you are still welcome to join this session. Don't mind. Okay, go to the next question. For you are not member of CIRED, are you aware the existence of CIRED Nation? Are you aware of the existence of the agency called CIRED Nation? So you got a few comments, but the story is not very clear. The voice imagine, sorry. I think got a problem with the mic. Okay, never mind. We go to the next question. May I know when do you get info regarding this webinar? From email, from bank, or either from direct message, or WhatsApp? Okay, thanks for all the response from everybody. Now we are continuing the program today to the next. So may I know, are you everybody aware about the current energy crisis? I believe it happens throughout a few countries, maybe the US. Oh, there's still a border group. A lot of majority of the participants is aware about the energy crisis. Okay, good. Because it's not happening actually, because it's not happening here. So maybe some doesn't bother. It happen everywhere outside Malaysia. So we go to the next question. Do you know the cause of the current energy crisis? The one for the answer yes. Do you know the cause of the current energy crisis? So we're still inviting everybody to join the poll. Just scan the QR or go to slido.com and answer the question. So for those who really know the cause of current energy crisis, let's go to the next question. Do you think the current energy crisis is happening now in Malaysia? Do you believe? Do you think it's happening in Malaysia now? Oh yes. Okay. Can we have everybody to join us for today? Just before we start our session. You got that. Okay, never mind. So, in one word, what do you expect from this webinar session? Can you share with us what do you expect from this session for today? Okay, good. Thanks for everybody's comment and answers. We've got some technical problem with my mouse. Okay. Sorry, got problem with the slide just now. Okay, sorry for the hiccup. Okay, we continue with the session today. Okay, for those who are not members, CIRED, let me explain just a short explanation regarding CIRED membership. So we have a few benefits. Once you join the membership of CIRED, you will get update of new technologies, latest technology knowledge in power distribution industry, as well as current practice for our MESI 2.0. We get informed anything regarding requirement of MESI will be informed to the members, and members are encouraged to give a platform to have open discussion on issue. Okay, how to become a CIRED member? You can join us by filling up the form and pay one-time entrance fee. So you can go to the CIRED website and apply for the CIRED membership. Okay, we besides this event, we also have a few webinar series in 2022. We have another 5 sessions in January, February, March, May, and June. And please take note of the dates. And we are welcoming everybody to join this session next year. Okay, we are welcome everybody to register for this event because we have put the link for the registration for the attendance form at the chat box. So everybody are welcome. Either can scan QR or just fill up the form by from the link forms. Please, you are advised to fill up your name as full as in IC, because we are they're given a certificate with the 1 hour CPD, eligible for 1 hour CPD. Please put your email and phone number for us to email and deliver your certificate, digital certificate later. So everybody are welcome to write up your name and send to us from this form link. Okay. Before we start our session, let me introduce the presentation profile. So our profile, presenter, sorry, got problem. Okay, our presenter today is Mr. Yang Zaidi bin Yang Zali. He is a specialist for transformer performance and diagnostic. Got a early education in degree and master in electrical. He have very vast 26 years experience in Kedah, Perak, and also in engineering service. His field of expertise is in transformer design and construction up to 33 kV. Also in transformer life performance, testing, diagnostic, and analytic, and also transformer related course in this. We have our own in-house training center. We call it Distribution Engineering Center for those who are not from TNB. Okay, the agenda will be today. We start with the presentation from Mr. Yang Zaidi for 30 minutes, and then we take a break for 5 minutes, and then we continue and for second part of the presentation with another 30 minutes. We end up with the question and answer session. Then and also at last we have a post survey at the end of the session. Okay, let me brief regarding the housekeeping rules. Every participants will be mute during the whole session today. All questions shall be asked using Q&A tools. Please provide your question in the Q&A tool. We will answer it later on, and kindly take a time to provide feedback. We have a survey and poll at the end of session. We are welcome everybody to give a feedback and suggestion for further improvement. And last but not least, focus and enjoy the session. So without further ado, I would like to welcome Mr. Yang Zaidi to deliver his presentation. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much, my dear brother, Haji Rashidi, and welcome to our TNB CIRED ACEM knowledge sharing on the topic of a review on transformer oil diagnostic using that dissolved gas analysis technique. So before I proceed, I would like to share TNB's experience in regards with dissolved gas analysis, because I know there are about 60 of us out there, and some of you are not from TNB. Perhaps it would be easy, or perhaps it would be more valuable knowledge to you if we can share some experience or some background on our experience on the use of dissolved gas analysis technique. All right, I think we have started what we call the condition-based maintenance by doing assessment on our assets, in particular transformers, since 2006. So since 2006, we have practiced oil analysis, which one of them is dissolved gas analysis. Since 2006 until now, I think we have gained quite sufficient knowledge in terms of the experience in managing our assets, in doing diagnostics and analysis, especially in terms of doing the interpretation based on dissolved gas analysis. So having said that, let's we move on to this presentation for today. It is a very general knowledge sharing presentation that I believe that if you are not familiar with transformer or DGA, I think you would be able to share or perhaps get the knowledge and try to understand much easier based on what we are going to talk today. Okay, first of all, the contents of my presentation, I would introduce to the first of the motivation or the issues on why DGA is very useful. And then we're going to look into the transformer failure types, a little bit of a background on dissolved gas analysis or DGA, DGA history in a timeline. We are going to look into the methods and technologies, and also the interpretation techniques that are available out there until recently. And then we're going to relate to grid of the future, as most of the utilities and industries are going into perfecting their system to become more info-related kind of system. And finally, we're going to look into the conclusions based on what we have discussed today. All right. So not a very pretty sight, this one, but this is something that most of presenters who are presenting on transformers or assets or condition-based maintenance would like to show in their first slide. So I am one of them then, showing you the consequences if we do nothing in terms of trying to improve the condition of our assets, in particular, in this case, are the transformers. So it is very important that all these consequences be avoided, and fault detection must be done before it is too late. So if you look into the history of major failures, these are some of the data collected by CIRED Work Group A 2.37 on transformer reliability. They have conducted this survey with the cooperation with a lot of countries, and they have populated this data. As you can see, there are some components which are ahead of the rest in terms of the number of failures. If we look at the location of the failure based on 964 major failures on your left-hand side, Okay, you can see the tap changer and HV winding as well as LV winding are the major cause or the major location based on this failure. Not to mention also about the bushings and the cause of this failure, as you can see on the chart on your right, is due to aging, to the design, but unfortunately, there are a high number of unknown cases also contributed to the cause of failure. So this is something that need to be further investigated so that we know what are the types of failure that actually causing the transformers to fail. So for those who are not familiar with transformers, I think this is a good slide for us just to kick off with the presentation. When we are talking about transformers, then we have, of course, the bushings. Of course, what we have up to 33 kV is not as huge or as long as these bushings, but this is what we call the HV bushing. And on that, on the other side, there is the LV bushing. Of course, we have the cooling and the diverter switch for the OLTC, tap selector for the OLTC. But what I'm interested to show you are the windings inside the transformer. Okay, so the windings inside the transformer are constructed as such that the HV winding are on the outside, concentrically wounded around the core, and the LV winding is in the center or inside the HV winding. Okay. So just now we looked into consequences if we do not do maintenance or assessment on our transformers. Most likely there would be a failure of or a fire due to the fault. Okay, so what actually caused these failures? We know that our transformers are operating 24/7, you know, every day, non-stop. And because of that, transformers are subjected to various stresses during its service life. So when we talk about stresses, we are talking about electrical stress, mechanical stress, chemical stress, as well as thermal stress. And furthermore, nowadays, due to optimization of materials, the size of the transformer is reduced. And because of that, the stress experienced by the transformer has increased. So the failure of a transformer will become even more expensive and quite unacceptable as compared to the cost to make sure that the transformer is in good shape. In other words, the maintenance cost. So it would be a good practice that we maintain our transformers, because if it fails, then the cost would be very, very high as compared to the maintenance cost. So let's have a look at some of the examples of those stresses. So we go first into looking into the electrical stresses. We have here the interturn shot on the LV windings, as you can see on the photo here. And then on this one here, it's a large transformer actually. This is a transmission transformer. Into this HV yellow phase winding shorted. And this is what we categorize as electrical stresses. Next are stresses quite normal actually to transformers. The thermal stress, okay? So transform as I mentioned just now that a lot of transformers has been, in terms of the material has been optimized, in terms of the size has been reduced. So as far as it is concerned, the thermal stresses has increased. You know, and I think that would be very true in the future as well. So as you can see on the screen right now are some of the effects of the thermal on the transformers. Some of the transformers fail finally fail but not because of the thermal. Of course, the final failure would be from the electrical due to flashover and so on. But the initial or the incipient fault that caused the ultimate failure in terms of the flashover and so on are due to or because of the thermal stresses that acting upon, for example, overheating due to eddy current in the middle photo there, or on the left-hand side, as you can see, the thermal heating of insulation paper due to high loading and poor cooling that causes the insulation paper to be very, very brittle and easily to fracture once there is a movement of the windings, perhaps maybe due to short circuit fault, whether very near or maybe very a distance away from the transformer. So next is the chemical stress. So there are a lot of factors that can cause these chemical stresses on our insulation especially. One of those are the copper sulfide deposition and corrosive sulfur that can give the effect in terms of the conductors or the contacts, and in this case acidity as well. If the transformer is not maintained and the acidity is getting higher, this acid will finally cause the insulation to break down, and as part of the byproducts, it would also introduce a moisture that could also be that could accelerate the formation of this fault in the transformer. Okay, next is the mechanical stress. So you can clearly see that these windings are deformed way beyond words actually. So if but of course there are terms or terminologies that are given to this kind of deformation. The one on the left is what we call the force of the hoop buckling, and then the free buckling, the one in the middle, and then we have the axial bending it's actually the winding collapse that you can see on the photo on the right. Okay, so these are what we call the mechanical stresses. These are no longer stresses, these are actually signs of failure on the transformer itself. Right, okay. So now we would like to go into dissolved gas analysis. But before we go further into dissolved gas analysis, we should take a note that the transformer, most of the transformers are, of course, filled with mineral oil. So my presentation today are mostly talking about oil-filled or mineral oil-filled transformer. And with this mineral oil that we have inside our transformer, it actually act as a medium that can provide us with a lot of information. So based on literatures, it is being said that the insulating oil contains around 70% of overall transformer operational data. So perhaps if we want to know the condition of a transformer, it is the best to take samples on the oil. So when we take samples on the oil, what can we do on these samples? There are, of course, three kinds of analysis that we can do. First is the dissolved gas analysis that we are going to talk about during this presentation. Then we can also conduct oil quality analysis, OQA, and the fluid analysis, FFA. Okay, so if you would like to know more on this, perhaps we can discuss this not within this presentation because of the time limit, but just to let everybody know that not only DGA that can be done, but also there are other techniques as part of the transformer oil analysis that is that is very helpful in terms of knowing the condition of our transformer. Okay. So when we talk about dissolved gas analysis and we talk about oil, so I think it would be a good example of, taking blood test, doing a blood test or taking a blood sample, okay? So we know that there are more than maybe now 50 or so kind of symptoms of diseases that can be detected through blood tests, okay? By just taking some blood tests, of course, you need to be injected with needles, which I'm not very keen of, to get the information inside of you, okay? So similarly, that is also a very good example of when you take an oil sample out of a transformer and send it to the lab. So what we can analyze is the diseases, the symptoms that could affect the transformer based on the data or that is available from the oil. Okay. So based on this information that we can extract to know the incipient fault or the fault, if there is any inside of our transformer. Because of that, DGA, dissolved gas analysis, is actually a famous or has gained a worldwide acceptance as a method for the detection of incipient faults inside of transformers. And then we are going to look later how we talk about dissolved gas. So where are these gas come from? Okay. So, but first of all, just understand that there are gases, and these gases are related to the faults, and somehow these gases or the concentration of these gases that is dissolved in the transformer oil can give us a lot of data, and that happens as a result of the composition of the insulating oil as well as the paper insulation. So right now, what we can understand is that these gases are the products of insulation decomposition. Okay, so but we are going to look into that in detail later on. Okay. So just now we talked about 70% of the operational data can come from the oil. By doing DGA, 50%, it is claimed that more than 50% of these incipient faults in the transformer can be detected through DGA. So that is actually quite helpful, as compared to perhaps doing visual inspection on our transformers. Okay, so what are the benefits of doing DGA? So let's have a look at one by one. We can assess our transformer without having a shutdown. We can use the DGA as a basis for advanced warning when certain faults are developing. And because we are talking about the incipient fault, that can give us an early detection to avoid failure and interruption. Of course, we can use DGA as our status checks on after we have repaired or we have done something on our transformers. So are we doing the right thing? So we can use DGA to know the performance of the repair that has been conducted. And of course, we can evaluate the thermal performance of the units, okay? In terms of the prototype units, because right now, if the transformer is to be conducted with temperaturized test, we can incorporate DGA into the test to know whether or not the design is what has been expected through the specification that has been specified for the transformer. Okay. So let's have let's think about something here. I think a lot of personnel in TNB, they are now very DGA is very close to their heart. I think most of them, they have done this, maybe they have gained experience for maybe more than 3 years, if they are still within the same section or units. That we know that DGA is very useful for slow growing fault. Okay, meaning that there is a fault growing inside the transformer that we can monitor, and we can do a trending of the gases that is produced due to the decomposition of oil or perhaps the paper insulation. And of course, because right now most of the practice on doing DGA are manual or offline, whereby we take oil sample and send it to the lab. And this kind of fault, which is slow growing, is very it's somehow suitable to the way that we are doing our oil sampling nowadays. But if you want to know because sometimes there are faults that occurred out of nowhere, what we call the instantaneous fault. Okay, no sign from historical DGA, no sign of whatever. If we are still depending on doing the DGA laboratory analysis by taking samples every 12 months or every 6 months, that won't help. Okay, what will help is, of course, to have an online sensor embedded in our transformer that have a higher chance that kind of warning before the instantaneous fault, we can know in real time, much sooner as compared to when we do the manual oil sampling. So so that is I'm talking in advance actually when we talk about these online DGA monitors. We're going to talk about that later in this presentation. But I just wanted for you to be aware that not every fault can be detected by DGA, even though 50% of the incipient fault can. But there is always faults out there that is instantaneous. So perhaps we need to change in terms of our practice to now install the online sensors for better monitoring of the condition of the transformer. Okay, so just now I mentioned about mineral oil that we are focusing in this presentation. I just wanted for you to realize that DGA is not only for mineral oil, it can also be performed and be interpreted for other types of oil as well, for perhaps for ester liquid, for synthetic ester, or perhaps silicon-based oil, and so on and so forth. So there are standards governing DGA for other types of oil as well. So not only on mineral oil, even though we are talking more on mineral oil, as you know that a lot of transformers population are still using mineral oil as their insulation and cooling system. Okay, how are we doing on the time right now? I just wanted to check. Let me check time. I think we are still on time. Right. A little bit of the history of DGA. I think it would be I think would be very interesting to some of you. Of course, the first transformer was invented in 1885, and that was a dry type transformer. But in 1887, a guy called Elihu Thompson had patented the use of mineral oil in transformer. So we can say that that is the cutoff year whereby mineral oil is used in transformer, okay? And then in 1880, Alexander Graham, I think it's Alexander Graham Bell, the same one, discover a photoacoustic technique that which will later be used to detect and also to measure gas molecules in from the oil. And then in 1903, okay, gas chromatography. So gas chromatography is a very important technique that has been developed, because without gas chromatography, or GC, in short, without GC, we in the early days of DGA, it won't help anybody, because this is the technique that able to do separation in terms of the gas molecules, to know what sort of gases are generated when faults are generated, okay, in the transformer. So actually the research in terms of this fault has come as early as 1919 actually. So there are a lot of papers, if you are interested in, talking about 100 years of DGA, for example, okay? So that's how long that DGA has been discussed in this world, actually. So so it is, I cannot avoid from mentioning about the gas chromatography. It was invented in Russia by MS Svet, I think his name. Maybe just proceed very quickly. I think the one which is very interesting, if we can relate this to DGA, is the invention of conservator tank in 1916, okay? Before that, a lot of transformers are using perhaps free breathing with air cushion or nitrogen cushion on top of their main tank. But as soon as they realize that the surface of the oil are in contact with the environment, and in a huge surface area, they decided to invent a small tank on top of the main tank, so that they can limit the surface contact between the environment and their oil. Okay, so with the invention of the conservator tank comes then the invention of book of relay and so on in 1928. But before that, in 1919 as well, there is the first observation of combustion gas evolving from insulating oil under electrical stress. So when we talk about these combustion gases, these are the gases that are actually above the surface of the oil, or the head space of the oil. So if I may relate this to this timeline, so from 1919 up to maybe 1950 to 1960s, most of the research are actually based on the free gases that are generated above the oil, okay? Not actually the dissolved gas yet. Okay, so a very interesting fact is that the first technique, or the first way that people do to test this gas is by igniting a match, which is very, very dangerous, to know whether or not there are gases as the result of fault within transformer. So these gases are actually from combustion gases. For example, hydrogen are very combustive. So this test is very, very dangerous actually. Okay, so then since they realize that these gas are generating from within the transformer, so Bukov is being invented by none other than Mr. Bukov himself. I forgot about the name, the front name of Mr. Bukov. And then in 1947, we have free gas accumulated in Bukov for the first time, and it is being classified. So here we know that it comes from, it is hydrogen, it's methane, acetylene, ethylene, etc. Okay. And then the gas chromatography technique or methods are perfected and more accurate. And since this 1960s up to 1970s are the time whereby GC are really being used on analysis of transformer oil. Before that, the test was done on petroleum-based oil as well, but not transformer oil. So, at the start of 1966, that I have made this research that GC is being applied to know the dissolved gases that is generated by the incipient for inside of the transformer. Okay, so as you can see there also there are interpretation technique of DGA are started. There are Donovan ratio being produced, and then they have this key method, the basic Duval triangle method, and so on and so forth. Okay, so I'm not going to elaborate more on this second timeline, but if you can have a look at the timeline there, roughly you can see the development of standards now within from starting as early as 1970s, and because of that, more and more people are interested in doing a DGA because of there are now standards that are governing these practices, and more people are coming with a lot of ways to interpret the dissolved gas analysis or the gases that are accumulated over the time, and because of that also the technology to detect or to measure these gases are also in progress and developing, and until now I think it doesn't just stop here. I think new ways of finding a better technique will be there in very near future. As you know that when we talk about GC, the gas chromatography just now, conventionally it is a technique used in laboratory, but not anymore. This technique are also being applied for online or for portable equipment as well. Okay, right. We are going deeper now into DGA. I hope you are still there and still looking at my slide and not dozing off, I hope. So we talked about just now the generation of gases due to the composition of paper insulation as well as the oil. Okay, so where these gases are coming from. So this slide actually answered that question. So it's actually coming from the decomposed oil or decomposed cellulose. In terms of oil, since oil is a hydrocarbon insulation, consists of hydrogen and carbon, whenever there is certain fault occurring inside the transformer based on its temperature, different kind of fault or gases will be generated. For example, if there is pyrolysis, pyrolysis is actually thermal fault inside of the transformer that causes the oil to break down and produce ethylene here, C2H4, and also can produce other heating gases like methane, CH4, or other gases as well. Okay, so if it is arcing, other gases, I mean ethane. Okay, so if it is arcing inside the transformer, it will cause the structure to break, and acetylene gas will generated inside of the transformer in the oil itself, which is C2H2. And if there is partial discharge of corona, it will generate hydrogen. Okay, so somehow this fault, when it is generated inside of the transformer, it is very repeatable. And this repeatable is very, very useful, because we can use this information not only on one transformer, but the whole population of transformer, because the patterns is there. Okay, the patterns are there. All right, so that's on the oil. So what about the cellulose or the paper insulation? So when there is a thermal fault, gases that can be produced due to that incident is carbon dioxide, CO2, and of course carbon monoxide. Okay, so these are the gases that are being produced as a result of paper and oil decomposition inside of our transformer. Okay, so just now I was talking about the types of gases, and these type of gases are produced depending on the temperature that the fault is giving, all right, or the fault is generating. So this slides is what it is trying to show here is that hydrogen, for example, can be initiated as at a temperature as low as 150 degrees, and it will increase as the temperature increases. Methane is around the same. It will also increase. Ethane a bit higher in terms of the initiation of ethane, and ethylene at 350 degrees. It would be initiated. Acetylene, what we call this arcing gas, will initiated if there is a fault that can cause a very high temperature of more than 700 degrees C. Okay, so this is the graph on the right is what we call the Hallstatt thermal equilibrium partial pressure. This describe the behavior of these individual gases against temperature. Okay, as you can see, the higher the temperature, different gases can be produced. For example, at the temperature as high as 1725 degrees, you can see the amount of C2H2 is increased from here going up to here. Okay, so these are actually just a general relationship between molecules and temperature, but there is a lot of literature out there that is now not too much disagree, but have some kind of comments in terms of the reality of this temperature to involvement of gas issue. But as far as it is concerned, most of the time, I think this graph is still works in terms of our diagnosis. Okay. So next, just a very brief, I would say, introduction. Yeah. In terms of what are the steps that should be taken when we want to do DGA, and what are those methods or techniques that are available in terms of each steps, and what are the standards governing each steps. Of course, if you want to do DGA, we must take oil sample, okay, whether manually or we put up a sensor inside the transformer. And these are some of the practice or equipment that is used, but I believe these some of these are quite obsolete. For example, they use perhaps the flexible metal cans, maybe in IEEE C57104 was mentioned in 1978, but I don't think it is mentioned anymore with the issue of C57104 2019. So we can, it is always being recommended if you want to do DGA to use syringes, because we can protect the oil, or perhaps, or most importantly, the gases inside the oil from being released to the atmosphere. And because of that, the results could be deviated and not correct, okay? So for gas extraction, there are several methods as well. We are talking about the vacuum extraction, extraction by stripping, the headspace sampling, the headspace meaning the gases on the top of the oil. And then this shake test, which is being introduced by Morgan Schaffer, I think it was in 1993. And then there is also a technology, a membrane technology, and a direct contact with oil. Most of the time, this direct contact with oil is to measure hydrogen or carbon dioxide. Okay, and the most important part of the whole process is, of course, the gas measurement. Okay, there are several technology up till now that is available. Of course, we were talking about GC just now, and GC was invented in 1903, remember? And it is still being used, and it is the most, I think, famous measurement method that is used, especially by a laboratory. But as I mentioned just now, it is also being applied to portable devices as well as online monitors. And then we have the infrared-based technology. Those are photoacoustic spectroscopy, or PAS, non-dispersive infrared, or NDIR. And then we also have the Fourier transform interferometers, or FTIR. And these are based on infrared technology, whereby the molecule of these gases are being heated up by this infrared, and with the help of filter, this infrared can be measured or can be detected in terms of the type of gas that is being analyzed within the unit, okay? And then there's, of course, also a technique called electromechanical cell, metal oxide sensors, metal film sensors. Normally, all these three, together with thermal conductivity cell, are being used with membrane or direct contact with oil, gas extraction technique. And later on, of course, we're going to look into the DGA interpretation methods as part of the diagnosis of the insulating oil. Okay. Okay, so let's move on to the most, I think, the oldest technique that is available for doing DGA, the GC, or gas chromatography. So these are roughly the gas chromatography. What you need to know is that gas chromatography uses carrier gas. Carrier gas can be argon, can be helium, can be nitrogen, okay? That is used as part of the mobile phase in this gas chromatography. And the most important part of gas chromatography is the capillary column, okay? Capillary column whereby there is also a static phase that is related to how the molecules of gas would behave whenever they travel along this very long capillary column, okay? And a part of also a very important device is the gas detector that is available as together with the with its GC, okay? So GC has been used quite extensively by UK Central Electricity Generating Board since 1968 and becoming more popular after IEEE guideline and ACEM standards as well as ASTM standard have been published. Currently accepted as the best digital techniques for measuring the concentration of gases of dissolved gases in transformer oil. Okay, if you have time to go to our TNB laboratory, TNB lab, you can have a look at this gas detection and measurement or GC device in the lab, okay, with the use of the carrier gas. I think in this case is helium. Okay, next is the photoacoustic spectroscopy. As I mentioned just now, part of photoacoustic spectroscopy is infrared-based technology, not in terms of discovery, as I mentioned just now, was discovered since 1800, okay? So quite an old technique that has been discovered, but it been used somewhere before, not in particular for transformer detecting DGA in transformer, but somehow it is being applied to detect gases that are being produced by this incipient fault. What is important here is that there is the use of the infrared to generate heating and thermal expansion of the gas molecules, and then the technique will also involve generation of sound wave that is generated because of the transformer heating, not the transformer, the molecule heating, because of the heating of the molecule, it become energetic, and somehow it will heat the walls inside, and there are microphones being installed to listen to this sound, that is the pressured sound that is made by these energetic molecules, okay? And that is what we call the acoustic detection of the molecules, so that we'll know, because each molecule behaves differently in terms of the way it hits and the sound being produced with the help with a filter wheel that have the wavelength selection that distinguish between one molecule to other molecule. All right, okay. So if you are interested to know more in terms of the technology available for gas measurement and gas extraction technique, you can make references to a CIRED brochure 783 that is produced or issued in 2019. You can have a look there on the extraction method and the gas measurement technology that has been compiled in this report, and what are the advantages and limitations of these technologies, especially when we talk about technologies that are going to be used as online monitors, okay? And then with the same brochure, you can also understand and try to get information in regards with what type of monitor are there, okay? This M8, M9, M7, M6, and so on and so forth are the category of the equipment in terms of the number of gases that it can detect. For example, here, the M8 or M9 type online devices can measure and detect hydrogen, methane, ethane, ethylene, acetylene, carbon monoxide, carbon dioxide, oxygen, and nitrogen. Okay, so there are about around 8 plus 1, 9 gases that can be measured with this M8 or M type monitor. So similarly, M6, M7 can measure 6 to 7 gases, M5 can measure 5 gases, M3 can measure 3 gases, so on and so forth. So later on, we're going to have a look at what would be the best type of monitor that we should procure or use for our own network or our own system. And having said that, also we need to know the possible faults that can be identified when by this technology or this technique in terms of the faults that has been listed down on the top left-hand corner up there. So, so these are quite important information that we can retrieve from the CIRED brochure 783 whenever we are thinking of buying or use online monitors for our transformers. All right. So I think we're going to stop here and take a break. I think it's enough for now. We are going to come back later on and have a look at further into DGA. So with that, I pass back to Haji Rashidi. Silakan Haji Rashidi.
Thank you very much, Mr. Young, for the very brief explanation. So we take a 5-minute break. But before that, let me remind everybody, we are welcome to register for this event. You are entitled for 1 hour CPD. You will get a digital certificate will be sent to you later. So everybody are welcome to fill up your details and just scan the QR or just click to the link provided at the chat box and fill up your full name as an IC, provide your email address so you can send digital certificate to you later. Okay, also courtesy reminder regarding CIRED membership, you are welcome to come and join us. Just go through the CIRED website or you can email to Puan Mashita as link with, at the bottom of the screen. Okay, we have a 5-minute break and we come back later after that. Thank you. We have a short video for everybody.
For more than 5 decades, ACEM's been focused on advancing professionalism and affecting change, because that matters to you as a professional, a consulting engineer. Regulations, status, influence and command. The Association of Consulting Engineers Malaysia, ACEM, has looked out for you through many milestones passed by our nation. Our quest started way back in 1963. Now we're headquartered in Kuala Lumpur with branch offices in Kuching and Kota Kinabalu. Come join us and be counted. Our goal is about empowering, looking into your interests, rights and privileges, availing a platform for your voice to be heard with the government, public bodies and industry associations, as well as extend cooperation with related bodies and stakeholders. When it comes to being a member of the Association of Consulting Engineers Malaysia, ACEM, it's about being involved and keeping abreast with our profession. From a membership spanning sole proprietors and partners of engineering consulting practices, ACEM is the reference point and influencing factor driving matters that affect consulting engineers in our country. With 900 individual members and 470 member firms, representing in excess of 20,000 employees, ACEM has the clout to become a formidable partner to be aligned with. We're heard in over 90 committees and work groups, and that includes ministries and local governments, government agencies, and related associations. ACEM's reach also ensures a voice in regional and international matters as well. Advancement of the consulting engineering profession is the essence of ACEM's existence. Working through standing committees and the Secretariat, ACEM continually provides a platform and paves the way, affecting and courting change. Our track record spans more than 50 years as a sole catalyst, augmenting the role of the consultant engineer. There have been many. The delivery of the Manual Perolehan Perkhidmatan Perunding 2011, which instruments the upward adjustment of government-approved salary scale. It was us. QBS as a government procurement policy. That was us too. Ad valorem stamp duty on construction agreements and BEM ruling on stamp duty. ACEM's insignia was clearly there too. And what about the future? Our relevance was also captured in the Green Building Index, GBI, for Malaysia. We believe in addressing what is needed. At ACEM, we believe that the consulting engineering profession grows in stride with ongoing global developments. We lead the torch in facing hurdles and charting the way towards a more efficient and effective profession. Because with ACEM, not one of our professionals gets left behind. Like a flame that never dies, ACEM is hard at work, overseeing and monitoring the landscape. Quite often, we're prompted to anticipate concerns and initiate engagement, like the implementation of the REA 2015, which allows liberalization of the industry, push for complete liberalization of consulting practice, urge for regulations requiring local participation in FDIs, promoting green initiatives in the built environment for waste reduction, resource conservation, sustainability of ecosystem, and improvement of quality of human life. Safeguarding fair and equitable treatment to all stakeholders involved in the construction industry, and encouraging technology adoption for the efficiency, productivity, and advancement of the construction industry. ACEM, for the betterment of future generations. Your participation is our advancement.
Okay, welcome back, and I will pass again to Mr. Yang to continue his presentation.
Okay, so welcome back to the second part of our webinar. So hopefully you are still energetic, as if you are being heated up by infrared out there. Energetic enough to listen to the second part of this webinar that we are talking on the topic of DGA, a review of this technique over the past decade, if I may. Okay. So before the break, we were talking about these methods, these steps and technologies that are available. And right now, what we are going to talk about is on the DGA interpretation methods. Okay, the DGA interpretation methods that are available, okay, since the start of DGA being introduced as a technique or a way to know the incipient fault inside of our transformer. So there are over more than 20 or around 22 DGA interpretation methods that has been developed. Perhaps there could be more, okay? As you can see, initially the methods are more towards the free gases that has been that is evolved and released through the conservator, through the book of perhaps. But later, there are techniques that is actually engaging in terms of doing analysis on the gases that is dissolved in the oil, from the Donenberg ratio down to Duval's triangle, Duval's pentagon, or Goda heptagon, and so on and so forth. So these are the list of the methods that are available out there. We are not yet talking about some laboratory that also has developed their own interpretation methods. Perhaps we are talking about laboratory such as Doble, such as TGH2B, and so on and so forth. Or Hitachi, okay, that have their own way of interpreting gas results from DGA. Okay, so when we talk about this interpretation method, and when we talk about also the review on this method, I think what would come to our mind is that which one would be the better or the best technique that can be used. Okay. For me personally, I would not look into that way, because each technique has been developed based on different samples, based on different condition, based on different criteria as well. So of course, some of the paper out there were talking about which one is more accurate, which one is more practical to use, and so on and so forth, or the best one that is available for use. But for me, I think it is not about the best. If you can use as many as possible, that would be even better. Okay, as if you are going to a clinic or hospital, you are not satisfied with the doctor's opinion, you want to have a second opinion, a third opinion, and so on and so forth. That is what it's all about, okay? Taking opinions of experts in the field to know what is going on inside of your transformer. So because as far as the papers out there or literatures that has been written on this are concerned, there is no winner, meaning that some people are saying perhaps this technique is the best, but some people is saying that this technique is the best. So there's no clear winner in terms of who is the best. But of course, personally, I have my own choice for that matter. But I would rather say that if you know all these techniques, use them, because the more the merrier, and the more information that you can have out of this technique, the more details information that I think you can dig up based on the real condition of the transformer. Okay. So let's have a look. So there are so many techniques here. Okay, we don't have time to look into all these techniques, and we are only talking about techniques that is related to mineral oil. Okay, let's have a look first in terms of a technique called the key gases technique. So when we talk about key gas, we are actually looking into the individual combustible gas that is being produced whenever there is a fault inside of the transformer. So on your left there, okay. So whenever there is overheated oil, there will always these heating gases that's going to be generated, methane, ethane, and also ethylene. If paper is overheated, as we saw in the previous slide just now, it will decompose and release carbon monoxide and also carbon dioxide. If we have partial discharge inside of our winding, for example, that will cause hydrogen, the oil to break down and generate hydrogen and methane. And if there is arcing, it will generate hydrogen and acetylene. And based on the distribution of these gases, you can see here on these bar charts on the right, the composition in terms of this distribution of gases are, for example, for corona or partial discharge, when we talk about hydrogen just now, and it is the major gas that is produced at perhaps lower temperature. And when you talk about overheating of paper, more CO or carbon monoxide being produced as compared to other gases. And when you talk about overheated oil, a lot of them may come as an indication from ethylene as compared to other heating gases. And finally, when we talk about arcing, we are talking about the generation of hydrogen and also acetylene in this kind of proportion. Okay, so let's have a look also in the key the development in this key gases area. Since 1978, IEEE C57104 has been developed, and this key individual gases has been given limits, okay, and this limit are being put as status condition 1, condition 2, condition 3, and condition 4. Okay, so what I'm showing you now are the version of 2008, a bit different as compared to the previous version, whereby the acetylene at condition 1, which is normal. Okay, condition 1 is the condition which is normal. If it is less than 1, it is normal. If it is more than 1, then it is not normal. Okay, condition 2, condition 3, and condition 4 are the condition which is not normal. Okay, but what is important here is that when we look into each individual key gas, as perhaps as a beginner, these limits are very useful. Once you are been doing this over the years, perhaps you may want maybe to have your own limits, for example, based on the experience, based on the data that you have. But initially, as a beginner, for me, these limits are very useful to let us know when to take some kind of action if we get certain results based, which is more than condition 1. Okay, right. Then in 2019, there's a new version of IEEE standard C57104 being issued. As you can see, not only one, but 4 tables has been produced. Okay, and most of these tables are taking the consideration on the amount of oxygen over nitrogen ratio. At table number 1 on the 90th percentile, there's this oxygen and nitrogen, oxygen, nitrogen, oxygen, nitrogen. But what is actually the importance of oxygen and nitrogen ratio to the development of fault? So what I can say here is that this ratio is quite useful to know sometimes in terms of fault that is occurring in a reduced thermal condition, or perhaps as you can see just now on the previous slide, we were talking about fault that is generated above 300, above 700, and so on and so forth. Perhaps with the use of oxygen over nitrogen, we can also look into more details in terms of fault that is generated with less thermal effect. And also with this ratio also, we know that oxygen and nitrogen are part of the composition of air. And in normal condition, we can say that the ratio between nitrogen and oxygen are fixed. But whenever oxygen especially been consumed within a transformer, then we can see that this ratio will be different or will be reduced. And because of that, that will also be very useful in terms of finding out what is happening inside of the transformer. Okay, so this is the key gases technique. Again, there's another method issued by CIRED called the table C7. This is a guideline by CIRED on the typical, the intermediate, and intermediate number 1, intermediate number 2, and pre-failure limits of these key gases. As you can see, when we talk about key gases, those gases are hydrogen, methane, ethylene, ethane, acetylene, carbon monoxide, and also carbon dioxide. Right, so next we are going into the ratio method. So ratio method is another method for interpreting the incipient fault within the transformer, okay? So this is what we call the IEC 60599 method. And the latest IEC being issued in 2015. Similarly, actually the first IEC interpretation method was issued in 1978 or 1977, as early as that. And then the second version was in 1991. The third, 2008, and the latest is 2015. I think they will issue another version in 2022, if I'm not mistaken. Okay, so this technique is based on the three main ratios that is used as an indication whenever a pattern exists to show whether or not there is partial discharge happening, whether there are discharge of low energy, whether there is discharge of high energy, thermal fault of lower degree, middle degree, or perhaps the highest degree, more than 700 degree. Okay, whenever all this ratio is indicating a positive sign of any individual gas. Normally, what we can get is one type of fault that satisfy all at the same time. For example, if there is a partial discharge, we can have this one true, true, and true. If there is discharge of high energy, and then this is true, as well as this is true. But maybe out of maybe at certain times we could see also some multiple fault, but that is very, very rare. Okay, next is Rogers ratio and Donenberg ratio, as you can see, these are quite an old system of or methods that's been produced to interpret the incipient fault. Okay, it also using ratios of these combustible gases. As you can see, I think there are similar ratio being used similarly by IEC just now. And also you can also see here, perhaps there's also there's also, the C2H2 over C2H4 is also being used by Rogers ratio. So both Donenberg and Rogers ratio is using, for example, the same ratio of of acetylene over ethylene, for example. Okay, but as you can see, the suggested faults are different based on the limits being given in this table, or the code being used by perhaps the Rogers ratio method, whether or not it satisfy the code that's been given for particular fault diagnosis. Okay, so next is the ratio on the Duval's triangle method. Okay, Duval Duval method was developed by Professor Michel Duval from Quebec, from Hydro-Quebec. There are a lot of triangles being produced by Professor Duval's, and this is one of the basic triangle that's been produced, if I'm not mistaken, since 1979 just now. Perhaps we can look again at that timeline. Okay. As far as it is concerned, this triangle is very, very powerful triangle. It only uses 3 main combustible gases. Those are methane, ethylene, and also acetylene. Okay, and this is how it is being calculated to get the percentage of all these 3 gases. And once the calculation are there, we can plot where the point is, and that will tell us whether the fault is partial discharge, discharge of low energy, and so on and so forth. Okay, so one thing that we need to remember, all this ratio technique that we are discussing just now can only be used whenever one of the gases are above or outside the limit. Whenever it is below the limit, you should not use this ratio, because it is as if garbage in, garbage out. Okay, we will still point out that there will be fault, but actually there's no fault. Okay, so use this whenever it is out of condition 1, if you want to use the limit of IEEE, or if you have your own limits, use your own limit. Whenever it is out of norms, then you can apply all this ratio technique to tell you in terms of the characteristic of the fault. Again, Mr. Duval, he likes to draw shapes and triangles and pentagons. These are his products. Actually, he has patented this product. I think he has patented more than 60 products altogether, if I'm mistaken. Okay, what I can share about these pentagons are the techniques that's been developed to know specifically the complementary fault. What are those complementary faults? The stray gassing, overheating, possible carbonization of paper, and also T3 in oil only, this SOC T3H. Okay, because normally, for example, IEC and Duval triangle, this one just now. Okay, there's only 6 faults being described. Here, there are additional faults that can be described by these pentagons. Okay, a very powerful technique as well. If we use this to complement the Duval's triangle, it will further tell us, especially this condition of SOC and T3H. For example, why is this, what is the difference between this T3H and T3? Okay, normally whenever there is heat being generated or hot spot being generated, there are possibility also there's involvement of a paper or overheated of paper due to the hotspot. Okay, so if we have that kind of situation, we can use this pentagon 2 in specific to tell us and differentiate whether or not it's T3H or whether it is C. Okay, so so that is one of the example of the benefits of using a dual pentagon 2. Okay, one of the point that I think I would like to highlight here is that the difference between D1 and D2. Okay, D1 and D2, what we call the discharge of low energy and discharge of high energy. Okay, this discharge of low energy or D1 is being defined as arc duration in a short time. Okay, so that a small layer of oil comes in contact with the arc path and is decomposed at its high temperature of more than 3000 degrees C. Whereby D2 or high energy discharge, normally this is an arc or arcing that comes with it the follow through current, which is quite high, but at a longer duration. Okay, one interesting point I think that is being highlighted here is that this follow through current will heat up a larger volume of oil through convection and produces a larger gradient of temperature in the oil around the arc path. Okay, and because of the area is larger, somehow it causes somehow the average temperature due to D2 as compared to D1 is lower because of the larger area that is involved. Okay, despite the higher energy content of D2, still it is producing at lower temperature because of the area that it covers, and because of that, producing a lot of ethylene in addition to acetylene as well. Okay, so those are some of the highlights I think I would like to share with all of you. If you look into this graph, I think you would understand the position of SOC in between T2, T1, and so on and so forth. Where does that develop into the versus the temperature that is available on the x-axis there. Okay, right. So we are not finished yet, even though the title has mentioned about the conclusion here. As far as studies has been done to know which is, like I said, people are very interested to compare, right? So some comparison has been done by CIRED in 2019, and according to the report, the IAC method and the other two gas ratio methods, such as Rogers and Donenberg, cannot identify faults in about 15 to 20% of DGA cases. So meaning that what they have done is they have done validation, whereby they have this DGA data and they have the actual case, and based on the analysis or the diagnosis of the interpretation, they compare it with the actual failure or fault condition. Somehow it is being mentioned here that IEC as well as Rogers and Donenberg deviate at about 15 to 20% of, as compared to the DGA cases. because of if you are if you have used this technique before, you know what it is talking about, because sometimes it is just out of the characteristic of the fault. It doesn't show any fault at all. Okay, so that is very different to triangle and pentagon method that's been developed by Professor Duval, whereby it has no limitations. Whatever that you are calculating, it will give you the fault. It will define you the fault. Okay, it will never give you something that is unidentified. Okay, it will always give you a result on the type of fault that is occurring inside of the transformer. Whether or not it's accurate, it is something else, but it will give you an answer. So that's the reason why this ratio is you need to know that it must only be used whenever one of the key guesses is above the limit. Okay, or perhaps the accuracy is above 10 or 15%. What I'm trying to say is that if you have perhaps, because in TNB we have nearly 2,000 power transformers, and we have 100,000 of distribution transformers. We don't have time to look into result which is less than condition 1, perhaps maybe even lower than 10 ppm or 5 ppm. But maybe out there in the industry, you are only looking at 1 or 2 transformer, even 1 or 2 ppm. You are very interested to know the DGA. I advise you perhaps you should go to do OQA or FUREN, for example, because in terms of accuracy, sometimes less than this 10 or 15 or 10 ppm could generate some kind of an error. And based on IEC, the accuracy should be more than 30% before you can use DGA method to interpret the results. Okay, so the basic requirement for using DGA, as I mentioned just now, is at least one of the gas concentration values in ppm is above the typical limit. Among these faults, stray gassing of oil are indicated as S, partial discharges of the corona type PD, overheating of oil less than 250 degree. So these are all the complementary fault characteristics that are newly developed, and most of it actually can be detected if we are using the pentagons developed by Mr. Duval. Okay. Carbonization of paper, C and arcing, for example, D1 and D2 in paper are potentially more dangerous faults, producing lower amounts of gases before becoming a threat. So what it is saying is that sometimes in the transformer, D1 or D2 has already occurring, but somehow in terms of the concentration of these gases are not pretty well detected, but somehow it is there. So what it is suggesting is that if in doubt, use that pentagon method so that if such a situation exists, then the pentagon method will be able to detect it. Okay. And then there is also issues on stray gassing of oil produces mostly hydrogen in mineral and silicon oils. These are some facts that has been gathered by the report of CIRED. And the last one, based on the report, the multiple faults that can be detected by the combination of triangles and pentagons. So again, triangles and pentagons, if you use them side by side, you will have more information in terms of those complementary or perhaps more detailed explanation in terms of the fault that is occurring inside of the transformer. Okay, So we have looked into and review methods of DGA for the main tank. Okay, for the so when we talk about the main tank, we are talking about the oil in that is flowing or circulating near the winding. Okay, now we are there are also methods or techniques being developed in terms of DGA for on-load tap changer for OLTC. In 2010, IEEE has released a standard called C57139, but in 2015 it's been revised with the second version, but more or less the content or the principle is the same. It's just that some information has been added, for example, in the annex of this guideline, Duval's triangle for OLTC has also been incorporated as part of the standards. Okay, so in any technique for interpretation of these gases, mostly you would come across a gas concentration and also the gas ratio. Okay, to be able before you can be able to interpret what sort of a fault that is happening. So in this case, for DGA for OLTC based on IEEE, it doesn't give us any limits, but it gives us the tools based on a mathematical model to find the outlier limit so that we can devise the limit based on our own population, which is quite interesting because you need to find the minimum 500, actually minimum 100 samples, the baseline samples, for you to be able to design or produce your own limits. Okay, so based on this gas concentration recommended by the standards, as well as the gas ratio recommended by the standards, in TNB we have developed our own limits. But before we go into that, here are some guidelines on before this limit can be applied to a population of OLTC, we need to know that there are similarity or in terms of the design of the OLTC. Otherwise, if the design is not the same or the classification is not the same, then the limit is quite useless. You cannot use the limit for a different design or different classification because the operation is different. The design is different. So you need to know, first of all, the classification scheme of the OLTC type. In TNB, for example, that we are using the one that I'm showing you on the right there. It is classified as ARAB, A-R-A-B, arcing switch with resistor type in oil immerse, where the switches are all oil immerse, and it is non-sealed because it's got a conservator. Okay. So I was thinking about the limits. So these are all the limits, the concentration limits that we have calculated based on the mathematical model given in the standards. And these are the limits for the ratio, the gas ratio. And based on these two concentration and gas ratio limits, we produce the interpretation of the results. And this is not mentioned in the standards. This is what we have devised based on our experience, and again based on the comparison with this one, with the Duval triangle. So when we do that, it seems that what we have done in terms of producing this interpretation is not far away from what Mr. Duval had devised based on its own triangle method for OLTC. So I think that's the reason why in IEEE, this triangle now has been inserted or incorporated in as an annex in that IEEE standard. So as a conclusion for the OLTC, so far, based on our experience, it is very useful. I think we have prevented a lot of near failure condition based on these techniques by doing this diagnosis. We can know the condition of our OLTC, and we arrange for shutdown, and we carry out a maintenance or overhaul on the OLTC. I think we have done that since 2011. I think most of the cases are well managed, but of course there are one or two cases that somehow not within the radar, or not because of it is not indicated by the DGA, but perhaps maybe lack of maintenance on our side. Okay, right. Okay, so having said that, we have reviewed all the methods, not all, of course, some of the methods of DGA interpretation. And we have also looked into the technology that has been used to for gas measurement and gas detection, which is very, very vital for DGA implementation. Right now, I think what we need to be aware is that what will happen in the very near future, and what will happen to DGA and to our transformers, because we are very, there are a lot of talks right now about energy transition, where we are migrating from fuel-based energy into more renewable energy. And as you can see, a lot of activities, a lot of things happening within distribution, and no longer perhaps within transmission or generation. There are a lot of distributed or DER in within distribution, and perhaps later on we're going to see even on the LV side, there are schemes that involve solar panels, the PV penetration, and how does that impact on the system. And of course, we also, there's a potential increase in terms of the use of EV, electrical vehicle, and how does that will impact our transformer, especially in terms of loading and so on. Something that we need to look into, and I think something that it is happening very close to us, because it is happening within the distribution itself. And because of that, I think we cannot afford not to have no information anymore in terms of what is the status of our assets, in this case, transformer, for example. And the key to know this is, of course, through digitalization of our transformer by using the online sensors that we were talking about just now, on what would be the best sensors to use based on, later on, based on what kind of monitoring that we are interested in, okay? So I think this is very interesting. I think in the future, there are talks that later on, perhaps DGA in terms of laboratory will reduce dramatically in a way, and the use of online sensors are going to um, take the stage and be part of the vital implementation in terms of DGA, especially. Okay, right. Okay, so if we want to know what would be the best solutions for our system, for our transformers, there are a lot of technologies as what we have seen just now. I'm not talking about brands. There are a lot of brands, of course, with different kind of packages and prices. So if you were responsible for your own system, which one would best suit your own network or your own system? So in CIRED report, again, I'm actually referring to the previous CIRED report, brochure 409 2010. It gives some guideline on the application of the online gas monitors that perhaps you are looking for. Okay, are you looking for abnormal gassing and fault identification? Are you looking for B for abnormal gassing, for example? Or are you looking for load monitoring with minor faults, or false gas alarms, or E, actual oxygen consumption? Okay, because you need to know, because there are different brands out there which is looking at different number of gases. For example, if brand one is looking is measuring only one gas, normally hydrogen. Brand two is measuring two gases, normally hydrogen and carbon monoxide, and so on and so forth, until brand number 7, 9 gases. Okay, so naturally, the more the number of gases being measured, the more expensive it is. So you need to know which one that you want to apply, and based on this report, it is given clearly what you should expect. For example, monitors for application A, B, and C are particularly useful in strategic transformers. Transformer used under overload condition where power cannot be interrupted for economic reasons. Transformer in nuclear power station. I don't think this applies to us anyway. Where catastrophic problems may occur in the case of power disruption. Transformer that have a large economic impact on the facility. There are more actually being listed in the report. I think you can make a reference to it later on. For maybe monitors for application DE, useful for transformer with regular overheating problems, free breathing transformer with frequent gas alarm, for sealed transformers to detect air ingress into the transformer. So you need to know what sort of application that you're looking for, and whether or not you need to have the complete number of gases, so that you need to make a complete or a full diagnostic. Perhaps you just need hydrogen, for example, just to give you warning. So these are the questions that you need to answer based on the specific case for your own system. Okay, so these are one of the places whereby we have installed our DGA monitor in TNB. We have more of this later on as well. A major advantage of online monitors, of course, it can detect abnormal gassing and faults occurring in real time, or perhaps near real time. And then our samples for DGA in laboratory or with portable monitors are taken mostly from the bottom of the tank. So this is some notes actually. If we were to take all samples for our manual monitoring program, we normally take the samples from the bottom of the main tank. Okay, but for the online monitors, it is more practical to connect it from the top going down to this monitor and going back to the bottom, because as we are talking about gases being generated here, so these gases are more, there's a tendency it will rise into to the top instead of going to the bottom. So it will be more logical to install this monitor coming from the top and going back to the bottom. And lastly, the interpretation of DGA results in transient cases should take into account the non-uniform distribution of gases in oil. So what it is talking about is actually whether you're taking it from the bottom or from the top. The main factor is that when it is in equilibrium, it doesn't matter. So when equilibrium is reached, gas concentration and composition are the same, whether you're taking from the top or from the bottom. So to get into equilibrium, normally the transformer is energized for in a long period of time, whereby the load is also being more stable, and of course the temperature is also more stable, so that it creates the equilibrium within the transformer. And when that happens, it doesn't matter actually where do you take the sample from, but it's more practical for online DGA to take it from the top. So these are basically the some sensors that you can put. I'm talking about DGA here. There are also other sensors that can be used to complement DGA in a way. We have this maintain DGA, we have this OLTC DGA. Other than that, we also have, there are, of course, other methods or technique available to complement DGA. Okay, so having said that, I have come to our final presentation here. In conclusion, I think what we can say here is that DGA has become the most powerful tools that can help us in terms of knowing the status or the condition of our transformer. Secondly, there are several measurement techniques for DGA are now available out there, whether or not using the gas chromatography, or whether it is using infrared-based technology, and so on and so forth. So many technology are now being developed. What we need to do, of course, we need to evaluate them. And how are we supposed to do this evaluation? Normally, we are comparing it with the laboratory results, but of course, sometimes laboratory result is also not accurate. So when so in CIRED report, it has give a guideline on how to manage comparison and how to manage these results between the online as well as the laboratory results, which is very, very useful in my opinion. And finally, in regards to the techniques being used for interpretation of the results, again, I would suggest that if you can use as many as possible, please do so, because it will give you more information. If you, for example, if you know that now that Pentagon can give you even further details in terms of your analysis and diagnosis, please do so, because the more the merrier, and one technique alone doesn't really be the best technique. So what I'm trying to say is that if you prefer to do perhaps Dovel, at least you should do another one or another two just to compare your results, methods of interpretation, so that before you make any decision, you know that you are on the right path. So having said that, that's the end of my presentation for today. Thank you very much. So I pass back to Haji Rashidi.
Thank you very much, Mr. Yang Zaidi, for the very informative presentation. Actually, it's not the break now. So we have end to our session. Before that, we go to the Q&A or question and answer session. So unfortunately, until now, I haven't received any question from the rest from the viewer out there. But I have a question to Mr. Yang. So based on the interpretation from the DGA, most of the interpretation shows only for one fault. So how we can manage to get multiple fault from this DGA interpretation? Mr. Yang?
Sorry, can you repeat the question, Haji Rashidi?
My question is normally for each DGA interpretation, for example, Duval or Roger, only show one or single fault from the guest. So is there any option we can get multiple fault from the interpretation?
Thank you very much for the question. Normally, from my experience, the incidence of having multiple faults is very, very rare. If that happens, that could be the results of the actual fault instead of the cross having two type of faults causing the failure. But it is not to say that it is impossible, but most of the time that it is the cause is normally from a single kind of a source. But to say that it is going to be that all the time is not correct. But what you can do, of course, is to use, like I said just now, if you somehow found that based on one technique, it is showing you multiple faults. But if you use, for example, Duval, that won't happen at all. Duval will only give you just one result or one fault characteristic. Perhaps maybe if you are using IEC, or perhaps you are using Rogers ratio or Donenberg ratio, you might find that somehow it is not within the interpretation at all. And normally, when this happens, people tends to categorize this as multiple fault. But like I said just now, use as many tools as possible, so that you will be confident in terms of what is actually the cause of what caused the fault actually to occur within your transformer. So that will be my answer.
Okay, I got a question just now, but I got some problem with, since I shared the screen, I couldn't read the whole question. Okay, I'm not really sure who is the. I got the question from Mr. Azam. So the question is, do TNB do online monitoring for all of their transformer, or maybe can share the percentage which using online monitoring?
Actually, we just embarked on a project, a pioneer project on using online monitoring. But just to tell you the history of this online monitoring, when there was an initiative of the on the grid of the future, I think it was 5 or maybe more, 5 to 7 years ago. All these online devices or techniques are still quite expensive actually, and because of that, it is we we were just in the position of doing studies in terms of when it is being used by our grid for transmission. So what we are saying here is that we look into the application of using the technique, and we found out that most of the time we need to know the full diagnostic of the fault, if any, meaning that the application is the A application, if you remember. So if you were to have this A application and we need to know all these 8 or 9 guesses to install the same unit on a transmission transformer as compared to a distribution transformer, somehow the ratio of the cost is a bit bigger on our side. So that's the reason we just recently started using applying this online monitoring technique. Especially right now, we have our own agenda of becoming the smart utility in distribution.
Okay, thank you, Mr. Young, for the answer. Since I have got another 2 questions. Okay, how to balance between cost optimization, spend OPEX by conduct different test method, and find the root cause of the problem? Maybe the panelists can share the best strategy and priority of type of tests can be conduct if you want to troubleshoot the problem, to troubleshoot the fault.
Okay, thank you for the question, and it's a very interesting question, but it's not an easy question, I should say, because what we need to do is we need to come up with the complete CBA, or the cost benefit analysis, and you need to calculate down to perhaps if a failure even occur, what would be the cost? And then I think you need also to compare the maintenance cost, the repair and maintenance cost that is being done regularly as part of your manual practices. And then you need to compare, if you install one online unit, what does this unit and the cost to install these units are cheaper than the ones that you than the normal practice that you are doing right now. So it's not really a simple question, but of course what I can say is that if you can list down all these itemized costs and you will get the answer to your own system and your own needs.
Okay, thanks for the answer. We got another 3. I hope we got extra time for to answer another 3 question. So the first question is from from Ozihan. Hi sir, would you like to ask for would like to have for your opinions on the practicality of this online DGA compared to the conventional transformer guard relay and CBM monitoring?
Okay, when we talk about the conventional transformer guard, we are talking about the book of relay in terms of the alarm. I'm not talking about the trip, because when it trips, it's no longer giving you an alarm. You don't have that luxury of doing something before it trip. So we're just talking about the alarm by the book of relay, and perhaps the transformer guard. I don't think you can regard the pressure relief device as part of your monitoring device, because it doesn't give you alarm, it just gives you only trip. So another, perhaps maybe the temperature alarm, that would be quite useful. Okay, if you compare this alarm to the online DGA, it is totally a different application altogether. because why do I say that? Because if you look into the temperature alarm, normally it will tells you in terms of whether or not your transformer uh, is loading normally, or loading under emergency loading, or perhaps cyclic loading of some sort, that causing the temperature to increase, or perhaps maybe the cooling system is not functioning, that causing the temperature to increase. But if you are using the online DGA in this matter, you are looking into more details of what is happening inside. For example, whether or not there is arcing, whether or not there is thermal fault, whether or not there is partial discharge, and so on. So, of course, there are relationship between the increase in terms of temperature to the to this incipient fault. As we know just now that we mentioned about this fault is most of the faults are temperature dependent. So as the temperature increases, perhaps due to the load and so on and so forth, there's a tendency whereby the occurrence of the incipient fault can happen. So, but actually, even though there's this relationship, but in terms of function of these two methods for online monitoring, they are actually looking at different different ways, if I may put it like that. And what was the other question?
The other two questions is, the first is, how about green oil or vegetable oil? Is it acceptable to be used?
Vegetable oil.
Yeah.
Okay. If you ask me, right now we are using mineral oil. Mineral oil is a fuel-based oil. So whatever is fuel-based is not renewable. Okay. So meaning that it is exhaustive, and one day it will disappear. So I think it's about time for us to migrate to use vegetable oil if we are serious enough in terms of, you know, the climate change, the global warming, and so on and so forth. So I think it is now. It's not in 30 years or 20 years time. It is now, if the technology is available, and of course you have also to consider in terms of the costing, the total cost of ownership, or the cost benefit analysis. It is about right, I think, and you have the opportunity to do that. I think please do so. Please use vegetable oil, because in terms of the technology, it is quite matured. For right now, it's quite it has come to its maturity as well. Right now, I'm talking about perhaps the synthetic ester oil. I'm talking about the ester oil, for example. But you need to know what are you using it for. Whether it is a seal system, hermetically sealed system, or is it an open conservator system. You need to know which vegetable oil to use. But as far as it is concerned, actually, in terms of the price, vegetable oil is much costly. But of course, nothing comes cheap nowadays. You need to calculate, and if the calculation is right, and if the cost benefit is showing you that, yeah, it is time for you to migrate, please do so.
Okay, the last but not least, for the first question is there any method of how can we prevent from the existence of gas inside the oil?
I lost you there, Jirashidi.
Sorry, maybe some Okay, is there any method or is there any way we can prevent the existence of gas inside the transformer oil?
Oh, okay. That's a very interesting question. Remember when I put up few slides in the very beginning, we were talking about stresses inside the transformer and how these stresses are being contributed to the reduction in terms of the size of the transformer and in terms of the optimization of the material used. Okay. Why I wanted to relate to this is because in our experience, we have a very old transformer manufactured maybe 60 years ago, and based on DGA, almost every year when we do the DGA, there's no always condition one, meaning that there is no gases that is generated above the limit. Of course, we cannot prevent from this gas to be generated because the transformer itself is operating. When it operates, it also produces heat, and then we are talking about loading and so on and so forth. And of course the voltages that give you the impact in terms of stresses. Okay, so we cannot stop these stresses from acting upon the insulation or the oil, but this old design somehow has got a lot of oil inside, is bigger than its own rating, meaning that as if it is a luxury house, only two people is living inside. So it's a luxurious design, and because of that, perhaps the stresses in terms of the thermal stresses is reduced, but again, it's not preventing the gases from generating. There are some gases generating, but still within the limits.
Okay, thank you very much, Mr. Yang, for the answer. And again, thank you very much for everybody to submit the question. So before we end our session, we have a survey, quick survey. So we welcome everybody to join us. Please, okay, you can join us through the website slido.com. Just put the hashtag CIRED and please insert the passcode TNB. And we welcome everybody to join to give some feedback or comments regarding our session today for improvement for a few sessions later on next year. So the first question is, what is the timeline? What do you think about the timeline for this webinar? Is it too short or is it too long, or do you think it's adequate time? Please, we have until now we have only 3 participants. We are welcoming everybody to come and join. Okay, thanks for the one who support us with the answer. So we go to the next question of the survey. What do you think about the presentation today? Is it effective or is it easy to understand? If you think it's strongly agree, you can mark the first one, or you can probably you just answer it very well. So okay, thanks for everybody who submit your answer or your. Okay, we go to the next question. Are you understand with the content of this webinar? Okay, thank you for the answer. So we go to the next question. Are you interested in participating in the upcoming series of webinar organized by TNB or CIRED? We have another 5 sessions next year in January until June. So really need to know, everybody is interested to join. Okay, thanks for your answer or for your response. So you go to the last, in your opinion, or we are welcoming opinion or comments from this session for our better improvement for upcoming webinar. Please share your opinion and comments here. Okay, before we end of the session, just another reminder about another 5 session in webinar session in 2022. We have a webinar on Bitcoin mining, energy transition in February, PQ Task Force in March, IEC 61850 in May, and last but not least, distribution automation in June. So everybody are welcome to join this 5 session later next year. So we come to the end of the session. We would like to thank to everybody who joined the session and give the response. And before you leave, can you share your emoticon or emoji? Okay, thank you very much. So until we met in, before you leave, for those who not registered yet, you can submit your details. Just click to the link provided at the chat box. Okay, thanks very much. Until we meet again later next year. Thank you. Bye.
Thank you. Bye-bye.
Kau sentiasa gerangi hidupku, kau sentiasa sinari duniaku. Indahnya cahayamu, indahnya kehidupanku, sentiasa TNB di sisiku. TNB menjamin sejahtera, TNB penjana cahaya. Indahnya cahayamu, indahnya kehidupanku, sentiasa TNB di sisiku. Kami sentiasa berkhidmat pada negara dan rakyat dengan komitmen yang tinggi. TNB berkualiti, cahayamu bercahaya di serata negara, terang menerangi, sinar menyinari, better brighter. Cahayamu bercahaya di serata negara, terang menerangi, sinar menyinari, better brighter. Kami sentiasa berkhidmat pada negara dan rakyat dengan komitmen yang tinggi. TNB berkualiti, cahayamu bercahaya di serata negara, terang menerangi, sinar menyinari, better brighter. Cahayamu bercahaya di serata negara, terang menerangi, sinar menyinari, better brighter. Terang menerangi, sinar menyinari, better brighter.
Auni?